this problem we are going to solve a prismatic steel bar of length 2 meter and Young's modulus of 210 gigapascal is subjected to an axial push of 70 kilonewton, which is we are saying as a allowable stress. If the shortening of the bar is limited to 0.4 mm, find the suitable radius of the bar. That means we need to find out the radius of the bar. Assume a factor of safety of value is 3. Also find the stress and strain developed in the prismatic bar. So the given data are a length of the prismatic bar. Let us take this is a prismatic bar. This uniform cross section we have, that is a prismatic bar. So we have cross section, this is a cross section. And length is 2 meter. So we'll change this as in 2000 mm. And Young's modulus 210 gigapascal. So we have to change this gigapascal Newton per mm square. So 210 into 10 to the power of 3 Newton per mm square, right? And this load is 70 kilonewton, and we have to change this is 70 into 10 to the power of 3 Newton. And the another thing is factor of safety FO is equal to 3. And shortening the length is limited to the given value, right? Shortening of the length, that means change in length is 0.4 mm. We need to find the radius of the bar. So we have, it is a circular one. So the given data is it is circular rod, right? It is actually the why, because we are finding the radius of the bar, right? So we need to find the radius, and since we have the values and factor of safety, though we need to find the radius of the bar. Before that, we know the deflection formula due to the stiffness, right? Deflection into PL by AE. This already we've seen, right? So from this only we have to identify area, all the things are there: change in length, original length, strain, load, and area. From this area only we will get the diameter. From the diameter we will get the radius, right? So we'll change this as in terms of area. So keeping A here, we have PL by this deflection into E. Area we can write it as pi by 4 only the d square equal to PL by pi A equal to P. This area we getting here, PA equal to PL by delta and E. So area we can write it as pi by 4 d square PL by delta E. Right? We know the diameter, so only we need the diameter. So diameter squared we keep it as, so we'll send the remaining term 4 PL by pi, changing into this one. So we have the values for what is the P value? P value here, so we have the P value here 70 into 10 to the power of 3. What is L value? L we have 2000. All the units are in mm divided by, this is 3.5, we know the value 3.14 into change in length is 4.5 into Young's modulus 210 into 10 to the power of 3. If you solve this, you will get you will solve this here. So 4 into 70 into 2000 we have. So we have into 1 divided by into 1000. So divided by pi, divided by 0.4, divided by 210, divided by 1000. So we have the value of diameter square equal to 79 0.788456. So if you take a root of this value, and you will get diameter equal to, this is diameter. So if you take the divided by 2, you will get radius r equal to 3989422 mm. If you take this radius square, then you have to put the root of this value, then you will get 79.99. So we identify the value of radius r. The remaining part is we need to find out the strain and stress value. So finding a stress value, normal stress, that is load by area, that is allowable load. We have the given data. So we have the allowable load 70 into 10 to the power of 3. Area is pi by 4 by d square. We have the d value. So 70 into 10 to the power of 3 divided by pi by 4 into 79788, the whole square. If you solve that, you will get 14 megapascal. So that is the stress value is 14 megapascal. So we got the another value. Third one is strain value we need to find. Strain equal to change in length by original length. Change in length 0.4, original length we have 2000. Then we will get 2 into 10 to the power of minus 4. So we will try, always we will change this as into micro strain. So we will multiply it into multiply divided by 100, so that we get 200 into 10 to the power of minus 6. This minus 6 only we will write it as 200 into micro strain. Right? So in result, first one we got radius r equal to 39.89422 mm. Second one is we got the stress value 14 megapascal. Third one is strain, that is 200 micro strain. Right? We'll do the revision. So in prismatic bar, they give us prismatic bar. This is uniformly cross section, but they give the Axial radius, so it is circular bar. So given data L equal to 2 meter, Young's model they are given, load equal to 70 kilonewton, and the factor of safety they are given. And from this only we are identifying that radius of the bar, which the given data are, we have the deflection equal to formula we have PL by AE. From this data we are identifying A, keeping P and L here, we are getting delta here and here. So area we are replacing as pi by 4 d square into PL by delta and TE. So only we are keeping d square pi PL by 4 PL by pi delta into E Young's modulus. So we are substituting this, we are getting diameter and taking the divided by 2, we are getting the diameter. Here you have to, from d square to d you have to square it. Square it you have to take down. So then we are finding the stress value, stress equal to load by area, load we have, area we have. We applied this and we are getting the stress is equal to 40 megapascal. Strain equal to change in balloon length, we have strain value small change in length, the original length we are getting 200 microstrain. In result we identified radius, stress and strain. Thank you.